Yeah, it's okay.
Is it going?
Yeah.
All right. So, any questions so far on this sand cell? Okay. So, we talked about the sand settlements and the time dependency of it, which we usually don't talk about settlements in sand in terms of something being time dependent. But it turns out that there are all these different factors of creep, a little bit of secondary consolidation, and the dissipation of pore water pressure, and the distortion in sand particles that results in some dependency on time. So you saw in the previous examples that if you get 2 inches of settlement immediately after the settlement, after the construction of the building, you may get an additional inch of settlement after 30 years. And 30 years is a pretty long time. So that's what we get for sand. But what about clays? What is the primary difference between sands and clays? Drainage, and what does drainage cause in terms of the transferring load from skeleton to, or transferring load from the system to the soil skeleton? What do we call this transition of load from pore water and the whole mixture to soil skeleton?
Consolidation.
Consolidation. So the main difference between sands and clays is that in clays we get quite a large amount of consolidation. And I want you to check this when you're doing your homework 3 assignment, because homework 3 you have a settlement calculation in sand, and then you have another problem, settlement calculation for clay. And for clay you have to break it up into the immediate settlement and the consolidation settlement. And after you're done, I want you to compare the amount of settlement that you get from the immediate settlement to the consolidation settlement, and kind of compare it for yourself to see if that consolidation settlement is large or not. And I would tell you that that consolidation settlement should be pretty large. So that is why when we get to page 16, settlement of shallow foundations on clay, we have to break it into immediate settlements and consolidation settlements. Whereas in sand, we just kind of lumped it all together by adding that F sub T factor that took care of the time factor. But in clays, we have to break it up into 2 different ways. The immediate settlements on clays is what described on page 16, and I want to very quickly just flip through the pages to see where we're going at. So page 16 is the immediate settlement on clays, and then if I flip the page 17 and 18, these are again on immediate settlement on clays. And there's an example on page 19 for immediate settlement on clays. And then on page 20, we start consolidation settlement on clays. So going back to page 16, we have a few pages of the handouts to go through the immediate settlements on clays. And it starts with the Janbu et al. 1956 equation. This is one of the very common equations that we use in practice for consolidation in general, and specifically, I'm sorry, not consolidation, settlements in general, and specifically settlements, immediate settlements in clay. And let's look at the equation. W equals I0 times I, what is that, I1? Multiplied by Q times B divided by E of U. What does this equation remind you of? The elastic equation, right? The one that was on page 6. The elastic equation is exactly the same equation that we have here. So the Janbu equation, Janbu et al. 1956, or the immediate settlement of clay, is really nothing new. It's basically the same elastic closed form solutions that we already discussed about. So what do we need to do with the elastic solution? Find those influence factors, I0 and I1. If you remember in the elastic equation, we called it I1 and I2. Here we just call it I0 and I1. We had the same I's in the sand equation too, the Bearland and Bearbridge equation. There were all those shape factor, depth factor, all those factors that were basically representing these influence factors. So what we need to do is to find the influence factors, those two. And then we also have to find Q. That's easy. The structural engineers already give that to us. It's either the factor load or the on-factor load. B is the dimension of the footing. Again, we already have that. And in the denominator is that E of U, or the undrained shear modulus or undrained elastic modulus of soil. Why does it have U? Why does it have an index U?
Undrained.
Because it's undrained. Because when we start talking about clays, everything is undrained. For most of the loads that we are dealing with in analyzing clays are slow enough for the time that it takes for the pore volume pressure to dissipate in clays that they're treated as undrained. That's why it has that U index. So we have to figure out a way to find the EU, or the undrained elastic modulus of clay. But we already did that for sand, so this is probably not too difficult to do it for clay. And then we also have to find those influence factors. So let's keep going through these variables. WI, there's an index I there to emphasize that this is the immediate settlement, and to remind you that you're not done by using this equation. You also have to calculate the consolidation settlement and add it to the settlement to get the total settlement of clays. And I underline this here. It's an average immediate settlement under flexible foundation. For sand, we didn't really get into the difference between flexible and rigid, and whether if it's the average or it's at the center or the edge. And I don't want you to get bogged down with that, because that equation was based on empirical equations, based on those 200 stories, all designed for factor safety of 3, blah, blah, blah. So they were, what they gave as the settlement was just an average settlement. And some of those cases may have been flexible foundations, some of them may have been rigid foundations. We don't want to get into the details of those. But the Jambu equation for clay, these are elastic solutions, so we can really separate them into flexible ones and the rigid ones, and for flexible ones we can look at the edge of the foundation, the center of the foundation. But for us as designers, now we've got to a point, we've passed those conceptual elastic solution design. Now we're getting into the practical equations. The sand equation is a practical equation. You plug in the numbers, you get the settlement, you report it to the structural engineers. This one, same thing. It's a practical equation. So they've averaged the settlements at the edge and the center, and they came up with this WI, the average immediate settlement under flexible foundation. I sub 0 is layer thickness factor based on figure below. So if you look at this figure, that's the Q. B is the width of the foundation, D is the embedment, H is the depth to the firm layer, or again, I'm just going to call it bedrock. I'll add a point here that it doesn't have to be bedrock or rock. In local practice, a lot of times people refer to a type of soil unit as the competent soil. Yeah, so it's a very local geotech knowledge, depending on where you're working at, what that competent soil is. Sometimes it's a very dense soil that is considered as firm enough that it's not going to have any settlement. And they could be rock formations. Here you might have toileton formation. You might have different types of formations that are bedrock, or they might just be a very dense gravelly sand that we just assume that will not contribute into your settlement. So firm layer or a bedrock. And then I0 is found using this figure here. So on the horizontal axis is D over B. D is the embedment, B is the width of the foundation. I assume you already know this, but B and L, which one is the smaller dimension?
B.
B. So if you have a strip footing, your B is 2-3 feet, your L is 100 feet or something. So the dimension that we plug in here is the smaller one, the 2 feet, not the longer dimension. And then we read I0 from this figure. Then we go to the other influence factor, it's a shape factor based on again, this figure below. So on this figure, vertical axis will give you I1, the horizontal axis is H over B, and all these different lines here are L over B. So if L over B represents a strip footing, L over B equal to 1 represents square, and circle is also 1, and you see that they're pretty close, so they're kind of like over there, and then as the ratio increases, these lines keep going up. So you have your H over B, you have your L over B, you read the I1, you already have I0, you plug it into this equation, you already have your Q, you already have your B. What is remaining to find? It's the elastic modulus that remains to be found. So E sub U, undrained elastic modulus of clay. I'm going to underline that undrained over there. How do we find it? Let's flip to page 17. On top of page 17 is the same discussion on QB versus QB net. You already have this, so we're skipping this. Are we all comfortable with the difference between Q and QB? Yeah? Do you have any question on this? Milad covered this on Thursday. So. All right. So if there's no question on that, we go to the next one, a note on obtaining E sub U for clay, or undrained elastic modulus for clay. Similar to sand, we have different options to find it. We have the lab test. We have, so that's one lab test on field samples. We have 2 in situ tests. We have 3 correlations. And we had the exact same categories for sand too. We had the lab tests, which we said they're not very useful for sand because once you sample it, you lose all those field characteristics. And we had in situ tests, and we had the correlations or those presumptive values that we looked at one of them from Ashton. So similar approach. Let's look at the lab test. Lab test on field samples. Now here we're talking about clays. Can we get relatively quote-unquote undisturbed samples on clay? Answer is yes. It has a high cohesion, so the particles keep it together. Once you sample it, you retain some of those in situ characteristics or field characteristics of the soil. For example, triaxial test is one of the things that you can do. So an example is shown here. You take a sample, you subject it to sigma 3 or the chamber pressure, and on top of that you add that deviatory load or delta sigma d on top. The length of the sample in the triaxial test is L naught, that's the initial length, and then if you plot delta sigma d versus axial strain, which axial strain is defined as delta L divided by the original length, you get a curve that looks like this. Now, the slope of this line gives you the elastic modulus, just like how we said it in sand. Now, in sand, we had one problem, that the slope of this line was dependent on sigma 3, so it was stress dependent. This is now clay, so we have less complexities to deal with because it's not a stress dependent problem. But we have to figure out something to do with the non-linearity of this curve. This is not a linear line. So if you're at smaller strains, your elastic modulus is this line. But as you go towards higher strains, your elastic modulus decreases, right? And you get to the secant modulus. So your E, or elastic modulus that has to be plugged into the settlement equation, is a strain-dependent modulus. And that makes it complicated because we're trying to find strain in order to find the settlements. So if I don't know my strain, how am I going to find E? And that is why this becomes an iterative process. So, and then there's another complexity to deal with. So again, for sand, we had this complexity that it was stress dependent. So depending on what stress the soil is underneath, is under with, the curve was different. And basically referring to, let's see which page that was. Here. So on page 10, we talked about how different sigma prime freeze for sand will result into different curves. For clays, we said that we can sample it, but no matter how you sample it, you can never get a completely undisturbed sample. There is always going to be some disturbance in the sample. And turns out that the sample disturbance changes the curve that you get in the lab test. So if you get higher disturbance, as the sampling disturbance increases, you get a curve that is softer. But if you get a fairly undisturbed sample, the curve gets higher. So your lab test, you have to include this uncertainty in your calculation that the E-value that you get is not spot on. It could be, there is quite a bit of uncertainty in the elastic modules that we calculate. And how do you account that as a designer? Let's say you're sitting in your engineering office, your job is to calculate the settlement, and you've already sent the sample to the soil lab, they send you this curve, and you measure the elastic modulus of this curve at the target strain that you want as, I don't know, 100 KSF. How do you deal with the uncertainty in design?
You modify it by some factor.
Exactly. You apply some factor safely and reduce and increase the elastic modulus. The kind of the art of doing that is to know how much you have to modify, and that's the experience that you gain, or the more experienced practitioners can tell you how much off you could be in terms of elastic modulus. But you modify, let's say you have 100 kPa, maybe you reduce it by 50% and you plug in 50 kPa, not kPa, kPa. You input 50 kPa and 150 kPa. So you add 50% higher and 50% lower, and then you do your calculation based on that, and you give a range of settlements to the designers, the structural engineers. So that's the lab test. Now let's go to page 18 for Insitu test. Same stuff. We have the the Insitu test that we have. We have pressure meter tends to be very good estimate. Tends to give you a very good estimate of elastic modulus in clays. That's the one that I think I told you we have a pretty strong expertise at PSU using pressure meters, and we have some of those devices. And because PSU has been pretty strong on pressure meters, the local practice in Portland and Oregon has used this device quite often in projects. So pressure meters is one of them. Dilatometers, plate load tests. I'm not going to get into the details of these, but these are different types of in situ tests where you can do the test on the soil in situ, in the ground. And shear wave velocity measurement. So I didn't write down the equation when we talked about the shear wave velocity previously for sand, but that's the equation. Vs, or shear wave velocity, is the square root of G, or shear modulus, divided by rho, or density. And the shear modulus is related to elastic modulus. You can, I always, every few months I Google shear modulus versus elastic modulus, and the first thing that shows up on Wikipedia is an equation that relates shear modulus to elastic modulus as a function of Poisson's ratio. And you've had that in your mechanical materials, or solid mechanics class too. So you go from G to E, and you're done. You have your E elastic modulus, you plug it into the Jambu et al. Equation, and that gives you the settlement. And then we get to the correlations. So because the elastic modulus has all these uncertainties in how to measure and estimate them for sands and clays. For sands, we have to deal with the disturbance and the stress, and in clays, we have to deal with the gain disturbance and what strain level we want to calculate it. We often rely on correlations and presumptive values a lot. One of the main correlations that we use is this equation here. It's known as the Duncan equation, and EU, or the undrained elastic modulus, is a function is equal to K times SU. What is SU for clay? Undrained shear strength. That's the one that we've been talking about in the past couple of weeks. Should be fairly comfortable in being able to calculate it. So you have your SU, and then you multiply by this constant that is obtained from this figure. This is a very useful figure. I've used it many times in practice, and it remains to be one of the most commonly used correlations for clay. So the horizontal axis is over consolidation ratio. If you're NC clay, what is your OCR? It's 1, and if you're an OC clay, that OCR increases to 10. Some of you had this question about the problem 6 in homework 2, that you were asking what is the range of reasonable OCRs, because you were getting really OCRs for the first row of that Excel file. And you can kind of see in this figure that OCR ends at 10. And that's pretty much the OCR that you will see in practice. You barely see a clay with an OCR higher than 10. They usually range between 1, 2, 3, and they could very rarely get up to 10. So the reason you were getting that really large value is that you were calculating OCR for the sand row, which you shouldn't apply the OCR equation. But if you do apply, you get something really large, and that's an indication that you're doing something wrong. Either you're inputting the values wrong, or you're applying it to something that you're not supposed to apply to. So going back here, you have OCR here, and then these are different ranges of PI. What is PI? Sure you know it already, but plastic index is LL minus PL. So PI less than 30 is this range. PI between 30 and 50 is this range. PI more than 50 is here. And this K value ranges, between, depending on what PI you have, it could go up to 1400. And then you pick that K value, you multiply it by undrained shear strain, and that gives you the undrained elastic modulus that you need. Very practical equation and graph, very commonly used in practice. Any question? So, you want to get your EU, you look at this figure, you pick that constant K value, you multiply it by SU. But now you have another problem. What is your SU? How do you get your SU? Here's a note on determining representative SU. SU increases with depth. So how far deep should we go? If you go too deep, let's say you're designing a foundation with a width of 5 feet. How far deep should I average SU? Over 5 feet deep, 10 feet, 20 feet, 100 feet, 1,000 feet. As you get deeper, SU is going to increase. So if you average SU over really large depth for a 5 feet width foundation, you're going to get really large SU, and that will give you a very large EU, and you plug in a large EU in your equation, you get a very small settlement. So it's not conservative to get to average SU over larger depth. But what is the reasonable depth that you want to average it over?
2 times B, just like the sand?
Just, yeah, so, well, let's clarify that a little bit. So 2 times B is something that you can always go with. There's nothing wrong with the 2 times B. And that comes from that figure that we have over the I sub Z figure that shows that the influence of your strain diminishes below 2 times B. And that's a very good number to start. So in fact, if you read here, I have what Salgado listed for averaging SU over. It's a little more complicated. What I would go with is this. I think the Salgado approach is too much. It's splitting the hair. It's, you know, we have other uncertainties in these methods, and that's too much refinement. I would just go with that 2B distance below the base of the fluid. But just to clarify, in sand, we used something a little bit different, and that was that influence factor. So if I flip back to page 13, we had this ZF0 depth of influence, which wasn't quite 2 times B, it's less than B. And can you, just for the sake of discussion, would you think that a smaller depth of influence, is it more conservative to assume a smaller depth of influence or a larger depth of influence?
Smaller.
Why?
For clay, you're going to get a smaller EU, which is going to give you more settlement, right?
Exactly, for clay and sand. For sand too, I mean, this example that I had here, N60 was kind of constant, but in reality, N60, you've probably seen in the other examples that we had in the problem, it increases. So if you assume a larger depth of influence, you're going to average a whole bunch of large values at depth, and that will increase your N sub N60, that will reduce your I sub C, and that will reduce your settlement. Same thing with clays. If you average it over a larger depth, you're going to get larger SU, that will give you larger EU, and that will give you smaller settlement. So you have to pick something that is reasonable. And 2B is something that is very commonly used in practice without getting into too much details. But Salgado uses something that's a little more detailed. You can read it, but I would recommend using the second approach. Any question?
Are there any obvious cases where you would want to be more conservative and not go with 2B and you would use like 1.5 or something like that?
Yeah, here's an example. Let's say you have a soil, a ground surface, and you're building your foundation here. And let's say your foundation is 5 feet width. And let's say you have a clay layer here, and then you have an NC clay, and then you have a very high OC clay underneath, very large over consolidated. So your SU profile
it's just going to skyrocket when you hit that high clay.
Exactly, it's going to skyrocket. You would be kind of here, here, and then all of a sudden, once you pass this point, it's going to be here.
And so that the normally consolidated clay is going to settle quite a bit, and if you start taking into consideration that OC clay, which may not settle hardly at all with the new load, then it's going to skew your settlement quite long-term settlement.
And let's assume that these depths, let's assume this is 7 feet. Okay. So if you want to go with 2 diameter or 2B, that's 10, which means you would have to include these high SU values. That's going to skew your SU to be higher, lower settlements. If you want to be more conservative, you would probably want to assume 7. Yeah. Good question. Any other questions, comments? All right. So let's look at an example. Page 19. Find immediate settlement of the footing under the applied structural load. Again, I'm repeating it over and over. It's a clay, so you have to calculate immediate settlement and consolidation settlement. Right now, you're only calculating the immediate settlement. The foundation is given, it's a 40 feet by 80 feet foundation. QB is given, it's 2000 PSF or 2 KSF. Some parameters of clay is given, it's a clay CL. What is CL? I have it written here. Low plasticity clay, right? PI ranges 10 to 30. Gamma is 120 PCF or 0.12 kpf, kcf, that should be kcf. New Poisson's ratio 0.5, OCR 1.524. And the SU is given here, so it increases with depth. And you see here, so the embedment is 10 feet, and then you have 160 feet of clay. So this is going to be your H, this is going to be your D. And to average SU, we are going 2 times B. So B is between 40 and 80. Which one is B?
40.
40. So 2 times 40, that's 80. So I'm going from 80 feet below, so 10 to 90. And I average these, and you look at these values, it's almost 5 KSF, roughly. So then you can plug in the values. You have, that's the equation. H over B is this, L over B is that. You go through those 2 equations, you get the I0 and I1 value, and then you have to estimate elastic modulus using E over SU chart. So PI is less than 30, that's given, it's between 10 to 30, and OCR is between 1.5 to 4. So let's look at the graph, the Duncan equation here. So OCR is between, 1.5 to 4, so we are from here to here. And PI is 10 to 30. So this is almost a 30 range. So we are somewhere here. So we have, values that are between here to here. What would you pick in this range? Well, let me ask you this. What would you pick if you wanted to be more conservative? Higher K or lower K?
Lower K. Because lower K is going to give you a smaller modulus, and so that would be more conservative.
Correct, yeah. So lower K will give you smaller EU, and smaller EU gives you larger settlement. If you want to be less conservative, you would pick a higher K. If you want to get the best estimate, you would pick something in the middle of this hashed area.
Like maybe
So
800?
800, yeah. 800 sounds to be pretty good. So that's what I've used here. So 800, and then SU, the average SU was 5, so you multiply that 5 by 800, and that gives you 4,000 KSF. You plug it into those equations, and that gives you 0.2 inch of settlement. Immediate or total?
Immediate.
Immediate.
And you mentioned earlier today, I think someone asked a question about safety factor. There's going to be a section on like adjusting these for like later, either next week or correct?
Yeah, I think probably next week. So next week we're going to start talking about the bearing capacity. And just to give you an idea where we are going with this. So for shallow foundations, we designed for 2 factors, settlement and bearing capacity. All these stuff in this handout is settlement. So you want to minimize your settlement to be less than some tolerable values. And what are those tolerable values? They're all on page 3. So you either go with these tolerable values and minimize your settlements to be less than these limits, or the structural engineer tells you that, hey, we designed this bridge, we can tolerate ½ an inch. Design a foundation that can settle less than ½ an inch of settlement. So it's either given to you or you go with those typical ranges. So that's the settlement part. But then on top of that, we have to design for bearing capacity. And that's where we usually apply the factor of safety. And we talk about the bearing capacity next 2 classes.
Is bearing capacity oftentimes the controlling factor in design?
Not necessarily. It could be bearing capacity or settlements that's
More
governed
difficult
the
to
design. Yeah, it could be either. trying to remember the cases that I was involved. Yeah, we were usually asked to calculate settlements, but that's because usually the geotechs usually design for the bearing capacity. The bearing capacity is the first thing that they design for, and then we were specialized on the seismic aspect of it. So then the settlement would become more of an issue. So we don't remember too many cases where I did the bearing capacity calculation, but a lot of settlement calculation, which is heavily influenced by what's E or what's elastic modulus you. Any other question? So this basically sums up the immediate settlement of clay. And on page 20, we start the consolidation settlement. And so from this point, I'm going to ask you to start review. And I'm just going to go over the concept very quick, and you should probably already know it, but let's say that's the foundation, the pore water pressure is there, and if your water table is sitting at ground surface, the piezometer would show pore water pressure that is at the same elevation as your water table. Then you add the load, and where does the load go first? I'm sorry, okay, let's go back here. So before load application, oh, we go down, right here. Sorry. So then we apply the load, and where does the load go first?
Pore water.
Goes on the pore water. So the pore water goes up, and then we go from B to C. So during consolidation, the pore water jumps